methods for solving first order differential equation. Okay, so this is a standard form of first order differential equation, and it is having some initial value attached with it. So it is an initial value problem. That means y at the point x0 is taking y0. This form is obviously you are quite habituated with at this level. So we are just trying to solve this equation in a numerical procedure. That means we are not just following the analytical methods which we have learned till date, but following some numerical method. That means some process of approximation. Okay. So for the process of approximation, what we will do here, we will just consider the domain. That means the region where you are finding the solution. Say this y over this x range. Okay, x0 up to xn. Okay. Then what we will do, we will divide it into n equal intervals. Okay, small intervals. That means this h, there is a step length, okay, is very small. If I take xr equal to x0 plus rh, okay, then we will just apply an assumption. What is an assumption here? This fxy is approximately equal to f of xr minus 1 yr minus 1. That is fxy, value of fxy is approximately equal to the functional value at the point xr minus 1 yr minus 1, where you are taking x to vary within the range xr minus 1 to xr. See, first and foremost of all, what we are actually doing here, as I already said, I am dividing the whole region from say x0 to up to xn into this via these points into equal intervals, very small intervals. Then what we are doing, as I said, I am applying the process of approximation. So here approximation is what, you take any small interval xr minus 1 to xr. That means if I fix xr minus 1, then my xr is a neighboring point of xr minus 1. The gap in between these two is h, and we are saying h is required to be very small. How much small, or what is the degree of the smallness, that depends on the specified specification of the accuracy demanded in the problem. Okay, that we will understand as we go on through the procedure. For timing, h is very small. Up to this we can say. So if h is very small, then xr minus 1 and xr are very close to each other. That means they are neighboring points of each other, if we say like that. So we are assuming our function is such that this over this small interval, if you take any x varying within this small interval, the value of the function xy, value of the function f of xy, is nothing but the value of the function at the first point only. Xr minus 1 corresponding point will be yr minus 1. Okay, so the value of the function at xr minus 1 yr minus 1, that much assumption we are using here. So this is, as I said, key in the numerical procedure, obviously you are not going to get the exact result as in we usually get in the analytical method. Definitely there will be some error here. Okay, and that error is obviously because of this such type of assumption. Obviously f of xy cannot be exactly equal to this thing, so we are using this approximation thing. Not exactly, but approximately equal. And this is obviously quite a natural norm in case of numerical methods. Okay, so as soon as we assume this, now you see this becomes this solution, which obviously might be very difficult if we allow ourselves to follow the analytical methods. This solution becomes very easy. How? Just see here, as we take this small interval, so let us integrate this thing dy over this small interval. So obviously this is going to take part like this. So now you can just simply follow the usual steps, so as to get this result. Yr approximately equal to yr minus 1 plus f of xr minus 1 yr minus 1 into integration of dx over xr minus 1 to xr, because you are assuming this thing, so you are using your assumption here. So as soon as you use your assumption here, this is a constant quantity, so it should come out of this integration. Okay, that allows you to write like this, and ultimately you get this thing, because this is nothing but h. So yr is approximately equal to yr minus 1 plus h of f of xr minus 1 yr minus 1. So this approximation comes only because of our assumption of this approximate value. Okay, so we get like this. Now this iteration formula which we derive here has a specific name, that is said to be the Euler method. After the obviously the name of scientists who have derived, just found it for the first time. Okay, so if you are trying to find out what is yr is the value of y at the point xr. So if you are trying to find out the value of y at the point xr, then that is given via this iteration formula. So in now r is varying from say 0 to n, so you can Just find out y0, y1, y2 up to yn. Y0 is obviously provided to us, leave it. Other than that, y1, y2, yn, we can just simply find out. So if you can find out the solution, that is the y at every points over this whole region of your definition of the solution, x0 to xn, that means you are obviously finding out the solution over the entire range of the solution. So that means we have solved this problem, because for solving differential equation, what we have to find out? We have to find out y equal to some gx curve, and that you are finding out the value of this y at specific point y0, y1, y2 up to yn. So you are finding out the values at every point, and this y1, y2, yn corresponding to x1, x2, xn, this we are deciding which points to take, how much close to take. So definitely you just simply can find out this yr at this specific point which you want to find out. Okay, so this is the iteration formula under the Euler's method. Okay, so you just put r is equal to 0, 1 to n. For r equal to 1, you are getting y1. Y1 means y at the point x1. Y2 means y at the point x2, and likewise. So yn ultimately you are getting. So you are getting the value of y at every specific point of the range of the solution. So you are getting the solution. Okay, numerically. Okay. So this is the Euler's method. So if you just, as before I go to the problems, just see here, as I already said, this accuracy, obviously there is error because you are assuming something which is not exactly true or analytically true, but it is approximately true. Okay, so due to this approximation assumption, definitely some error will be there, and we can control this error. How? Via taking this point as much close as possible. Okay, so this age, the step length here is a crucial factor. If you want to increase the accuracy, you have to decrease the step length. Okay, so that is the thing. See, in the expression also you are getting this age. So you can well understand that this age should be meant lesser and lesser, so as to get more better and better accuracy. Okay, in fact, to get better accuracy, we will just see a few minutes after instead of Euler's method, we can use some better methods. Okay, so this is the first step towards the numerical solution of differential equation. Okay, so let us go to the problem one. Problem says dy dx equal to x cube plus y. This is given, we have to solve it. Acha, we have to solve it. Just read the question properly. This is the question given along with y at the point 0 equal to 1. Okay, you have to compute y at the point 0.02 via Euler's method. Okay, and now you see, correct up to 4 decimal places, taking step length h equal to 0.01. So in the problem, they are specifying the step length you have to work with, and what you have to do, we have to find out the solution at the specific point. See, if they do not specify the point, we cannot use the Euler's method. How? Why? Because you can just simply see what we are finding out via the iteration method. Y at a specific point. That specific point is not arbitrary. Obviously, it is belonging to the range of the solution, but this point should be specified. I cannot say y at x. It should be any of these xi's. Okay, so the question should be obviously of this form. You are trying to find, if you are trying to find out the y's value at a specific point, then you can use the Euler's method for that numerical procedure. And the step length they are specifying, so no question of getting better accuracy, you have to follow this step length. Okay, so then the method is very clear and trivial, because x0, another thing is that here obviously this is an initial value problem, because y at the point 0 is supplied to us. Okay, so x0 0, y0 1, these are all the informations given, and what is my f of xy? This is the f of xy. Okay, then y1 means h is your 0.01, x0 is 0, so your y1 is y at the point x1. What is my x1? X1 is 0 plus 0.01, so 0.001, sorry, 0.01. So y1 is nothing but y at the point 0.01, so you just use the formula. What is the formula? Y0 plus h into f of x0 y0. So it is y0 1, h is this thing, f of x0 y0 means here it is 0 plus y0 is 1, so this thing. Similarly, y2 you can calculate. So they have asked you to find out y at the point 0.02, so our problem ends here. Okay, Achha. And that's just showing if you follow the analytical method, you are getting this result. So now you see there is a difference between these two. So what is the error? This much is the error. Obviously, this error is obvious to come because we have used some approximation which is not obviously analytically true. Okay, Achha. Similarly, you can just go through this example also. Achha. Acha, before I go to this Euler's modified method, there is a better approximation method. Let me just discuss this geometrical significance of this, or geometrical idea of this method. How we can explain this geometrically. Okay. So for that, let me go into this part. Okay. So you are trying to solve this dy dx equal to f of xy. What we are doing, I am taking 2 points, xn plus 1. That means say xr plus 1, anything. Okay. So if you take like this, you draw a line segment. If you just remember what is our differential equation solution, we are actually there we engage ourselves to find out a curve such that you draw tangent at any point of the curve. The slope of the tangent is given by dy dx equal to fxy. That is, the slope of the tangent is given by a function value of f at the point xy. That is what we do when we say we are trying to find out the solution of a given differential equation. Okay, so here also suppose AB is a straight line drawn through the points x and y n. Okay, it is having a slope f of x and y n. Okay, Acha. So your point corresponding point, this is xn, this is xn plus 1. Okay, so this amount AC is h. That means you are taking two neighboring points. The difference in between these two neighboring points is h. Okay, and the slope of this line segment is f of xn plus 1, f of x and yn. Okay, now this much, if you see, you are saying in this point is x and yn, corresponding point, this is xn plus 1. You are drawing a line segment from x and yn up to the neighboring points b, which is xn plus 1, yn plus 1. So what is our main motive? Our main motive is to find out the value of the function or the value of y at the point x and yn. So what we are doing, we are drawing a line segment from x and yn to the neighboring point. Neighboring point will be obviously xn plus 1, yn plus 1, the next iteration, the next level. Okay, so this much BC is nothing but the difference yn plus 1 minus yn. If you take this is as yn and this much as yn plus 1, so obviously this is the case. So if this is the case, now you consider right angle triangle this thing. Apply the simple rule of this tan theta thing. Okay, so what you can say, before we go into that, this tan theta, I just use the notation an. Okay, so what is tan theta? Slope of the tangent. Here we are not considering any curve, so slope of this AB line making an angle theta with this x-axis, so it is the slope of this AB. So this is tan theta. We name it as an. This is nothing but, as I said, f of x and yn. Okay, because this f of x and yn we are not assuming. This is obviously there, because if you just, as I said, if you use the idea of solution of a differential equation, as I said, it is nothing but the slope of the tangent given via this function. This is obvious. This is an obvious fact. Okay, this is we are not approximating or we are not assuming on our own. This is obviously a fact when you deal with the solution of a differential equation. The slope of the tangent at any point of the integral curve is given by f of xy. So if my point is x and yn, then the slope of the tangent, if I draw this is my tangent to a curve, to the integral curve, then the slope is given by f of x and yn. Okay, at this point. So tan theta is f of x and yn. I name it as an. Okay. Now what is dy dx? Dy dx in the limiting condition is del y by del x. Okay. So now you use the approximation. I am approximating. If I am approximating, then this limiting condition I will let it off. That means I will not use it. Okay. If I am not using it, then del y is what? Yn plus 1 minus yn, and del x is what? H. But now you just use the right angle triangle. Yn plus yn, this thing, the difference, via the difference of this h. Okay. Then what is actual to? It is tan theta, but tan theta is f of x and yn. So this whole thing is equal to f of x and yn. That means an. So you just simply can write it like this. So you get yn plus 1 equal to yn plus h. An means f of x and yn. So this thing. So this is the Euler's method which we already discussed. So this is also an alternative way of understanding how this Euler method is coming into existence. Okay. Now let us go back into the modified form of the Euler method. Modified form. Achha. So what we are actually doing there, if you recall back, we were approximating the function f via using, say, the value of this f of xy is f of xr minus 1, yr minus 1, as long as you take your x to vary from xr minus 1 to xr. That is what was the approximation we used for the Euler's method. Okay, that means the most important thing what we did there, we approximated the function f of xy. Why it is the most important thing? Because that is the only thing which allowed us to take this thing out of this integration. Because this is the only thing which creates a problem. If you just think a little bit, this is the most difficult thing when we do the analytical part. If we do it, we solve it by analytical, it is not always the case that this is always integrable. It is always, it creates a problem. Okay, so as soon as we can take it out of this integration, our problem is done. Okay, so the approximation is the main thing here, approximation of this function f. Okay, so what we do here, if we follow the Euler's method straightforward as we did in the previous one, so this will come, right? We mark it as the first level of iteration, yr suffix 0. This 0 inside the first bracket indicates that is the first level or the initial level of approximation. Okay, of the value yr. Yr means y at the point xr. Now we know from the numerical integration ki any function can be there. We can have used this also for the trapezoidal rule. A function can be approximated via this also. So yr0 can be written in this form also. Yr minus 1. Let it be like this. I do not bother about this part. What I bother about is this part. Okay, so I am approximating the function. Just read this. Instead of considering f of xy approximated by f of xr minus 1 yr minus 1, we use the if we use the trapezoidal rule in that range, this xr minus 1 to xr, what I will get? This one, f of xy approximated by value, half of the value of the function at the initial point plus half of the value of the function at the final point. That means h by 2, hmm, f of xr minus 1 yr minus 1 plus f of xr yr. So this thing is coming if you use the trapezoidal rule. Okay. So now you see we are using another method of approximation of the function. Now let us see what change it will invoke or what change it will bring here. So as soon as we do this, in the next step of iteration or the next step of approximation or strategy, whatever you may say, what they are doing, key, this is your approximation if you follow the Euler's method. This is your approximation if you use the trapezoidal rule for the function f of xr minus f of xy. Okay. So what they are saying now, key, whenever you are trying to find out the, say, first level of iteration of this yr, you use the strategy, you replace this f of xr yr, that is this yr, via this yr0. That means you replace the yr via the yr which you will be getting if you use the Euler's method. That means yr0 equal to this expression. Just replace this yr here. Okay. Achha. So that is what they are doing. Now replacing f of xr yr by moderate approximation value, this thing. That means this, what you are getting, this yr0, you are getting via Euler's method at the end point of the interval xr minus 1 xr. That means at the point xr. That means then the first, second level of iteration, it is initial level, this is second level. That means yr1 is given by, this will remain as it is, this will remain as it is, plus f of xr yr you are putting there, here you will put yr0. That means the initial approximation of yr you will put here, and this is obtained via this Euler's method. So this is the new thing we are doing here. Okay, nothing extra. And one thing you see, when you are trying to derive the value of y at the point xr, definitely it is obvious that you have already found out the value of y at the point xr minus 1, xr minus 2, and back any point you take. Okay, so this yr minus 1 is known to you, xr minus 1 is known to you, yr minus 1 is known to you, so this thing is known to you, h is known to you, again xr is known to you. yr0 was not supposed to be known to us, but it is known to us as we are using the Euler's method before we do this yr1. So this is also now known to us, so we use that quantity here. Okay, so this is the modification part. Two modifications. First, instead of this approximation, simple approximation of fxy via this, we are using the trapezoidal rule for the approximation, and then using within that part we need this yr0, we are using here the Euler's method approximation rule. Okay, so this allows us to get this one at the yr1. Similarly yr(n), so yr2 what will it will be, yr2 will be yr minus 1 plus h by 2, f of xr minus 1 yr minus 1 plus f of xr yr1. So for yr1, what we will use? We will then use this thing. So in recurrent formula, I can write yrn in this form. So when you are trying to find out the nth level of approximation, you are using the n minus 1th level of approximation. One thing you see, for this one you need not use the Euler's method, because whenever you are, say, suppose I am finding out yr2, when I am finding out yr2, yr1 is already in our hand via this modified method, so we will use that thing, we will use that value. Okay, because Euler's method is not giving us yr1 or yr2 like that thing. Okay, so Euler's method is used only in the first step, only when you are finding out yr1. But in yr2, we will be using this yr1. In yr3, we will be using the yr2 we have found out. In yr4, we will be using the yr3 we have found out likewise. So this thing. So this n minus 1 is obtained via the modified Euler's only. Okay. And how long should we continue? You should continue, if you want to continue this approximation, you have to continue up to kth step if the k step approximation what you are getting is equal to the k minus 1 step of approximation up to the specified level of accuracy. So specified level means, say, up to 5 decimal places, up to 6 decimal places, as we are usually do in the numerical procedure. Okay, so if you get this to equal, then you stop here. So this should be your check step. Okay. Achha. So let us go into solve problems. So this is, you have to solve this. What are the informations given? Again, this is an initial value problem. See, this you can well understand here, key for the Euler's method or for the modified Euler's method, as the name goes here, you have to have in your hand some initial values. That means these methods are applicable for initial value problems only. If the initial value is not given here, we cannot use this method, because how are you going to get the y0 and the x0? You need it, na? Because without that you cannot approach. Right? So this is, you have to solve this. What are the informations given? Again, this is an initial value problem. See, this you can well understand here, key for the Euler's method or for the modified Euler's method, as the name goes here, you have to have in your hand some initial values. That means these methods are applicable for initial value problems only. If the initial value is not given here, we cannot use this method, because how are you going to get the y0 and the x0? You need it, na? Because without that you cannot approach, right? So you have to have this thing. Once it is the case ki this is not an initial value problem, then you cannot use these methods. We have to use in that a case, such a case, for the numerical method, you have to begin with something, that this initial value should be given here. Okay, so let us go to the problem. So this is the initial condition given. Acha. So what they're trying, that is the question, ki find y for x equal to 0.05. That means y at the point 0.05 and also at the point 0.01. So at 2 points you have to find out. Okay, correct up to 4 decimal places. So this is the desired degree of accuracy they are demanding here, taking step length h equal to 0.05. Okay, so step length is specified. Okay, so x0 is this, y0 is this, h is this. Okay, f of xy is this. So f of x0 y0 is what? It is nothing but 1. Okay, acha. Now putting r equal to 1, that is the first level, the initial level of approximation. Okay, and the second level of approximation, so y1 0. Okay, just without instead of just reading here, y r equal to 1, why you put here? Why? Because we want to find out y at the point 0.1 and at the point 0.05. You are taking the step length 0.05. Okay, and you are starting with 0. So if you add plus h, first you are getting x1 0.05. So what we want to find out here, y at the point this, that means you are trying to find out y1. That means yr for r equal to 1. That's why we have to take r equal to 1. This you have to understand which point you have to take depending on what they are demanding in the question. Okay, so we are trying to find out y1. So the initial level of approximation is given via Euler's method. This is this formula, y0 plus h into f of x of y, x0 y0. But f of x0 y0, as we already saw, just use this function which is given, x0 plus y0, x0 0, y0 1, so 1. So just simply find out y1 0. The initial level of approximation of y1 is 1.05. Now let us use the modified part, because for the modified part we needed this y1 0. We have already obtained it. Now let us use it. Okay, so the second level, that is the y1 1, the level of approximation. Okay, If I call this initial level, it is better to call this the first level of approximation, and it is the initial level. Okay, so the first level of approximation is using this formula. Okay, this formula. So what is this formula suggesting here? R is 1 as I suggest, so it is y0 plus h by 2 f of x0 xr minus 1 yr minus 1, so f of x0 y0 plus f of xr minus 1, so x1 f of xr, sorry, not xr minus 1, f of xr yr0, that means f of x1 y10. Just recall this back, this thing. Okay, so here y10, but y10 you just found out this thing by Euler's method, so use it here. So simply use it here. They are using it all this by putting all these values here and this getting this thing. This is 1. This is 0.05 by 2. This is again 1. Okay. Plus this point 1.05 for this y10 plus x1. What is x1? 0.05. Okay. So 0.05 plus 1.05 then. Okay. So this adds up to this thing. Okay. So now you have found out the first level of approximation. Okay, so we have to go to the second level, because if we do not go to the second level, how can we see whether we are getting the desired degree of accuracy or not? So let us go to the second level. So in the second level, we'll be using this value. See, as I already said above, key for the first one only you need the Euler's method. For the second onwards, we will use the modified Euler's methods approximate result. Okay, so let us see here y1 2. So again the same formula, y0, that means yr minus 1 plus h by 2 f of xr minus 1 yr minus 1 plus f of xr yr, first level of approximation. So everything is known. This is known from the previous step. This thing will be used here. See, 1.0.525. Okay. So you just add up. Now what you are getting, 1 point this thing, and what you got initial before that 1 point this thing, and what is your desired degree up to 4 degree of decimal places. After 4 decimal places, not degree, my mistake, 4 decimal places. So you are not getting it yet, because if you consider this round of thing, this is going to be 0.26, 1.0.526, but here you are getting to 5. So not the same thing. So we have to continue till y2, 3, y1, 3. y1, 3, you are getting exactly the same thing. Okay, that means if you allow your round up also, as we know, then also this remains the same up to the 4 decimal places, so we can stop here. So no further iteration required. Okay, similarly, what we have to find out next? So first one is done. For the next point, we have to add another h, that is 0.05. If you add with this, you are going to get 0.1. That means now we are trying to find out y2. So again, y2 at the initial level we will be find out by the Euler's method, then using that in the successive steps of modified Euler's method, as we just did for the above. So just go through it and you just get the answer what they are demanding. And you know where to stop. Here also in third level only we are achieving the accuracy, so we will stop there. Okay, so this is the modified Euler method. One another sum will be listed here, you can go through it. Okay, now is the Picker's method of successive approximation. Picker's method of successive approximation, what they are doing, this is yet another method of approximation. What they are doing here, you are considering this thing. As we said, our main and solo aim is that we want to avoid that integration part. So somehow we want to, you just want to get rid of that part. So what they're doing here, so x0 up to x you are taking, the whole range they're taking here. So just unlike the Euler's method, they are not dividing the entire region into small intervals of so xr minus 1 to xr. Like that thing they're not doing. They're taking the entire range, x0 up to x. X can be anything allowed within that range. That means the given range of solution or anything. Okay, that means x is adding here. Okay, and x0 is the initial thing which is given to us. Okay, so we can write like this, right? Now is the question how to tackle with this part. For the Picker's method, what they are doing, they are taking this thing, this integrand contains the unknown function y. As I said, this will be creating a problem. So this equation can be solved via the method of successive approximation, where the first approximation y1x will be obtained by replacing y by y0. Okay, so what, simple, straightforward. We want to get rid of this integration, just replace y by y0. If y is replaced by y0, so this becomes a constant, this becomes a function of x only. So now you can integrate, no problem in it. Okay, so once you integrate, you get some function of x on the right hand side. Now in the second level of approximation, you use This approximation here of the first step. Okay, let me just enlarge it yet. So here you replace for the first step of approximation, you replace by or you approximated by y0. The second one for y2, you will be approximated by y1. So whatever expression you are getting here, you will put it in here in place of y. So continuing this way at the n plus 1th level, you will be using the nth level of approximation. So this recurrent form is referred to as the Picard's iteration formula. Okay, so if you just note it carefully, you are just generating a power series of x. Okay, because x is there throughout. Okay, so variable is there, the independent variable thing is gone, the independent variable is there, and you are just going to generate a power series of x. Okay, let us see one sum. Another step, this is quite obvious ki for the iteration procedure, as we know ki depends on the how much iteration we should continue with, it depends on the accuracy level demanded. This is now obvious in our literature. Okay, so where to stop it, where you are getting the n plus 1th level and n plus 1th level approximately equal up to the desired degree of accuracy. Okay, so nothing new in it. So let us see this one problem. So use Picard's method now. This already we did before using the Euler's method. Now we are using the Picard's method. Okay, so this y at the point 0.1 you have to compute using the Picard's method. So x0 is this, y0 is this. This is, we will take at this y at the level of 0, that is the initial approximation. There is one. F of xy is this. So first level of approximation will be this. So here you see what we will do. We will use this function fxy. So x plus y. Here in place of y, we will put y0. So 1. So this becomes this thing. So now you integrate, you get this one. See, already some higher order of x is, higher degree of x is coming. So this thing. If you put 0.1, you are going to get this amount. Again, the next level, second level of approximation. F of x, y1x. So what is y1x? Y1x is nothing but, this is our y1x. We will put it here. Put it here means this is the function x plus y1x. Y1x means this. So x plus 1 plus x squared by 2. So this thing. Now you again you integrate, you get this thing. So again you put the value where you are required to find out. So 0.1 you find this thing. Till now there is not coming up to the, have they specified? No, they have not specified any accuracy degree. Whatever, then you have to continue for some. It depends. They definitely this degree of accuracy will be specified here. Okay. You need the y3x, you have to use the y2x, and likewise. So you see, you are generating a power series. Another thing you see, whenever you are using this y1x, you have to use this thing. Please do not confuse and use this one, because this is the value at the point, specific point 0.1. But here you are taking the functional form. So you have to use this. Okay. Similarly for the others also. So you have to keep that thing in mind only. Okay. So this you are done with. This is an example of Picard's method. Now let us go to the last one, the Runge-Kutter's method. The Runge-Kutter's method, let me just start with the RK2 method and just simply we can say from there the RK4 method also. Okay. So the advantage of this method over Taylor series method. Taylor series is nothing but you know how to use how to just decode the Taylor expansion. You can use that thing yx equals to, okay. So actually that is not much just beneficial to use the Taylor series method. So we use better this Runge-Kutter's method, where you also need not find the functional values at all points. Only some specific values is sufficient to deal with the method. Acha. The second order Runge-Kutter method, let us start with first, then we will explain the details of it. So this is the thing which is given to us. Okay. Now, first and foremost of all, this is nothing to do with the Runge-Kutter's thing. This already we know. Ki y double dash comes out to be this thing, y triple dash comes out to be this thing, and likewise. Okay, this is obvious known fact to us. Achha. Now, if you use the Taylor series method, or Taylor series, not the Taylor series method, but Taylor series expansion, that means at the point y, at the point x0 plus h, you can expand like this. I confine myself up to h square and take only the higher order terms. I'm not considering the higher order terms. That means this will give the error thing. Okay. So I stop here. So if you stop here, this is nothing but y0 plus h y dashed at the point 0 plus y double dash at the point 0. Okay. But y dashed is what? F of xy, it is given. Hmm? The y dashed at the point 0 means f x0 y0. Y double dash means this thing. The y double dash at the point 0 means fx at the point 0 into plus f at the point 0 and fy at the point 0. That means x0 y0. Okay. So this thing you can just write here and simplify it. So let us write and simplify up to this step. Achha. Now let us come to our method which we are going to discuss, the Runge-Gupta method. What we are supposed to do here, what we are planning here, see y1 I can write like this. Runge-Gupta method is saying, that means let us write y1 equal to y0. Obviously, if you are trying to find out y1, then I will use just the previous value plus k. Now this k I can decompose and or break in this form, alpha k1 plus beta k2, where k1 is of this form. There is a functional value at x0 y0 multiplied with the step length of x, and k2 is this form, again the step length multiplied with functional value at some other point x0 plus mh, y0 plus mk1. So here you are using, in k2 you are using the k1. So Runge-Kutta method is saying ki this breaking which you are using, I will just break it in two parts, and in one part I will be using the other part, because k1 you have just used in the first part, you are using it here. Okay. So this m, this n, this k1, okay, this alpha, this beta, okay, are all unknown. How to find these unknowns? Via comparing with this Taylor series method. Why Taylor series method? Because in Taylor series also you are finding on y1. Here also the same structure. So the right hand side of both should coincide. Okay. So in that case, comparing these two structures, this one and this one, we can find out. See, first one k1, what you are taking? F at x0 y0. So this thing, okay. So here alpha should be coming as 1. And alpha should be coming at 1. I cannot say why, because here you are getting f of x0 y0, and again you break here. Here also you will get x0 y0. So f of x0 y0. So f of x0 y0 is coming from here and also from here. Okay. So you have to add these two things up. So you get this first one. So you will compare the coefficient of f of x0 y0 from Taylor series and the coefficient of x0 y0 from this Runge-Kutta's assumption. Okay. So similarly, I will compare the coefficient of f of x at the point x0 y0 and f of y at the point x0 y0 from Taylor series and from the Runge-Kutta's assumption. That will allow us to go through the steps and get the values of the unknowns alpha, beta, m and n. Okay, so they are getting the values. If you take m, what turns out to be m and n should be equal. So it is your choice what you take. So they are taking m and 1 for the RK2 method. Okay, and alpha beta is coming out to be this value. So this is our choice, and this is what we are getting from these calculations. Okay. So once we get these unknowns, these were the 4 unknowns in this Runge-Kutta method. So just put it here, plug it in here. You are going to get the method. So what is the method in whole? y1 equal to y0 plus alpha half. So half k1 plus half k2, where k1 is f of 0, h of f0, and k2 is h of f x0 plus h, y0 plus k1, because mn you have taken to be 1. So this is your method in totality. Okay. And what is the error here? Error is h cube. Why h cube? Because what you are using in the Taylor series, you are taking up to second order, and third order you are not taking. Okay. And you are using this for the comparison part with the Runge-Kutta one. Here also, this approximation will be taking up to second step. Here, if you see, up to this one, K2, and not the further terms. Okay. So h square is involved, but not the other terms. H cube is not involved. So here it is order h cube. Error of the formula is order of h cube. That means the region for where you are truncating. Okay. So this is the RK2 method. And similarly for the fourth order Runge-Kutta method, exactly the same thing, that this procedure is same. What is the procedure same means? Here also you will assume something like this, where K is now decomposed into 4 parts. This is the structure. So order of the error is h5, because we will take up to h4, and then you have to continue comparing as we did before with the Taylor series, But here the Taylor series expansion should not be stopping at h square. It should continue up to h4 plus order of h5 you should take. Then as soon as you do that, you will get other terms here. So those terms again will be compared with the terms which you will be getting from this structure you are assuming. This one, here, here, here. Okay, because here also you can expand, here also, here also. Once you expand, you will get the higher order derivatives of this f function. You get here these things, and again you are getting here this thing. So you can compare to get the unknowns. What are the unknowns here? You have to get the unknowns. Here they have just simply put down the values. Actually, these are obtained via these methods MH sort of thing. Ultimately, you get this steady or this ultimate structure. They have written the ultimate structure here. Okay. So because of the tedious calculation, this calculation steps are avoided here. Okay. So what you have to keep in mind, this is the RK4 method you have to keep in mind, because it has to be used for your practical classes also, this RK4 thing. Okay. So before I go into this example part, let me cover this example part first. Nothing in it. If you are just going to now solve this differential equation numerically using the RK2 or the RK4 method, here they are using the RK4 method. Okay. So this is the thing given. You only have to use the iteration formula. Nothing in it. Okay. So this is the thing we are using. Okay. Another thing you see here, unlike the Euler's method, we are not using any iterative method here. It is not an iterative method, because in iterative method what we do, we go step after step. In the say a kth step or mth step, I am using m minus 1 as value. Okay. But here we are not doing that. It is not considering any of this thing. You are simply using all at a time. So here no iteration is involved as such as you did for the Euler's and modified Euler, or even on the Ficker's method. Nothing like that is involved in the Runge-Kutter's method. Okay. So simply, if it is given to you, you have to find out what they're just asking here. You find out the y at the point 0.4, and what is the initial value of x? 0. What is the step length? 0.1. So you have to find out y1, y2, y3, y4, because then only you will get y at the point 0.4, because yx0, yx1 will be at the point 0.1, yx2 will be at the point 0.2, yx3 will be at the point 0.3, so yx4 will be at the point 0.4. So you have to go up to that. Okay. So this is the formulas just directly using from here. Okay. x0, y0, this is the value, x0 plus h by 2, y0 plus k1 by 2. So k1, as soon as you find out, you can use here. H you already know, y0 already you know. So you just put all these things and you get this thing. K3, again you know K2, so you can use it here. Or again, this thing, and this are already known. So you can just simply calculate it. You get this one. K4, here you have to use K3. You have already computed K3, so you can use it here. X0, Y0, H are again known. So you can just simply plug in and find out this is the result. So once you find out all these constant, you just add them up according to the formula. 1 by 6 times K1 plus 2K2 plus 2K3 plus K4. So you simply find out y at the point 0.1 you are getting. So as soon as you get 0.1, now you have to approach for 0.2. So for the 0.2, I have to use whatever you have got for 0.1. So you see, that's why what I said, if I want to find out 0.4, I have to find out 0.3, 0.2, 0.1. Okay, other because without finding those, I cannot find this via this method. Okay, so 0.2 is obtained, then 0.3 is obtained. Ultimately, the required which they have asked for is obtained using this results, previous steps result. Okay, so this is the result that you are getting here. Okay, so you can just simply go into the other sums also. Okay, now let me just say a bit about the geometrical way of understanding the numerical method which you are getting for the Runge-Kutta method. Okay, RK2 I will be considering, and similar from the idea we generate how to get the thing for the RK4. RK2 method. What we did for the Eulers, hope you have already kept in mind we have drawn a segment, a line segment AB with the slope given by AN, that is f of x and yn. Okay. Now, for this RK2, what we do, we consider the point x and y in. We first draw a line segment of slope f of x and y n, that means a n, slope of ab, so as to reach the point, that means I am going from a up to b. Xn plus 1, I name this point xn b as xn plus 1, yn plus 1, tilde. Tilde, why? Because I have used this tilde notation so as to demarcate that this is not the thing which we are trying to find out. This is not the yn plus 1 which we require to find out. This is a intermediate step thing, intermediate quantity, which we'll be using further for our calculation. So we have used the tilde. Nothing other than that. That is the meaning of this tilde here. Okay. So AB. So I have drawn first a line segment of the slope f of x and y n. Now through A, let me draw a line segment of through A. Now let me just first finish it here. Through B, let me draw a line segment BC of slope f of x and y n plus 1 tilde. Now you see here tilde is used. Okay. So first I draw this. Okay. Then from B I draw another line segment having slope of f of x n plus 1 x and y n plus 1 tilde. Then what we do, through A I draw a line segment which is parallel to BC. Okay. Through A I draw a line segment which is parallel to BC. Then what I do, I take the angle between this new line, say A dash, I have used this A dash here, say A dash and AB. This, if it is theta, I take theta by 2. And then making an angle theta by 2, I draw a line segment AB dashed, having slope this much. So if it is a theta, and it is theta, and if I say it's theta 1, so theta plus theta 1. So I draw a line segment through A, AB dashed, which is making half of the angle with this AB. Half of the angle of this, if it is the whole angle, then half of this angle I am taking from here and drawing a line segment AB dashed. Okay. So this AB dashed will be giving the required slope. So first this was taken, then another line segment was drawn. This was of slope AN, AB, BC was of slope BN, and what we did through A, we draw a slope line AB dashed having slope SN. What is SN? Half of you are taking, so half of AN plus BN. That means half of this slope plus half of this slope. But this line is parallel to this one. So if it is having a slope Bn, so it is also having a slope Bn. So half of A plus half of Bn. So Sn is this thing. And if B dash is the point xn plus 1, yn plus 1. So now you see this point is xn plus 1, yn plus 1, not this point. That's why I have used this tilde here. This is the thing we require to find out, not this thing. So what we did here for the approximation part, or the drawing the slope part? Instead, if you compare with the Euler's, there we consider only this slope and used out the using the right angle triangle thing, we just calculated yn plus 1. But here we are not doing that. Here first we are drawing this, then again we are drawing another slope, then again we are drawing a slope parallel to this, and then taking the half of it. So actually you are doing two slope computation here, one for this one, another for this one. Okay, because this is nothing, this is you are taking exactly parallel to it. Okay, and then you're taking the linear combination of this slope and this slope. That means you're taking the linear combination of AN and BN. So you're computing differentiation, if you say, because slope finding is nothing but differentiation. So you're computing differentiation twice. So it is often named as the Runge-Gupta method, RK2, second order. If you recall back, I already said there you will be getting an error of order of h cube. That means in the Taylor's we dealt with terms up to h square. Okay. So here there also you took differentiation twice. Here also you are taking that thing, second order. Okay, that is the name suggests RK2 method. So once this is clear, then what you do, as we did earlier, here you now consider this slope as an plus bn by 2. Consider this triangle. Exactly this thing you'll be getting as we did before for the Eulers. So just use the values of Sn. That means this thing. So An is f of x and yn, and Bn is f of x and yn plus 1 tilde. Now what is this? What is the tilde? Tilde is the thing which we obtained at the very initial stage. How we obtained? Just by drawing a line segment having slope an, but this we already saw using the Euler's method geometrical part. This will be nothing but yn plus 1 equal to yn plus h into f of x and yn. So yn plus 1 tilde is nothing but the Euler's thing here. So we'll be using that thing instead of this tilde. See here, yn plus h by 2 f of x and yn plus f of xn and yn plus 1 tilde. Instead of yn plus 1 tilde, I will put the Euler's thing. Euler's thing means yn plus h into f of x and yn. So this is the thing. So this is the RK2 method. Okay. So let me, if you just see, you compare with the thing we derived using the algebraic method or the Runge-Kutta method, you are getting exactly the same thing. Let me go back. This thing. Here, h f of x0 y0, y0 plus h into f of x0 y0. Okay, half of h by 2 f of x0 y0. So here you are getting the first one like this, h by 2 f of x0 y0. Here they dealt with x0 y0. I am showing in general, so x and yn plus the second term again h by 2 into multiplied with this. What is that thing coming there? Plus h of x0 plus h, that means x1, that means xn. Acha, let me just say one thing. So plus and this yn plus 1. So y0 plus k1. K1 means, if you use this thing, y0, k1 means h of x0 y0. Right? That means f of x1 comma y0 plus h of x0 y0. So let us come here. Just one typo is here. It will be xn plus 1, not xn throughout. Okay. So just for timing, if I consider xn plus 1, so f of xn plus 1, yn plus h of xn yn. So exactly the same thing which we got via that Euler's method. RK2 method, algebraic way of finding. Okay. So this thing you are getting here. So this is right to here. It will be xn plus 1. Let me add up this comment here. It will be xn plus 1. xn plus 1. Okay. Not xn. The last term. So this is the thing you are getting exactly here. So let me add it here also. Here exactly. Okay. So this is how we can explain the geometrical way of finding out the RK2 method. So once this is RK2 method, for the RK4 exactly the same thing you are doing. So instead here what we took the linear combination of the slope like this. For the RK4 we have to take the linear combination of 4 slopes in this manner as they have demanded here, like yk, k1, k2, k3, k4, and this is the linear combination way. See here what was the linear combination way? Half of k1 plus k2. That means half of an plus bn if you compare with the geometrical thing. K1 f of x0 y0 as we just saw the similarity, and k2 likewise. Okay. So here you are taking 4 slopes linear combination in this form. 1 by 6, 1 by 3, 1 by 3, 1 by 6. Okay. So this is the thing. So you have to take the slopes accordingly if I want to consider the geometrical way of clarifying this RK4 method. So instead of an plus bn by 2, you have to take 1 by 6 an plus 2 by 6 bn plus, that means 1 by 3 bn plus 1 by 3 cn plus our 1 by 6 dn. Okay. So likewise you have to take. Okay. Similarly, you have to consider what are the terms given there, and likewise you have to draw the slopes and add them up. That means you have to draw a slope here, another slope from here to there, and ultimately you have to again draw that slope parallel to here, and ultimately you have to take the linear combination of all those angles according to the formula specified in the RK4. Okay. So this is it. Let us stop here. This ends up with the numerical method of the differential equation solution. Okay.